Hello everyone, we're ready to start. On the topic today, we'll say a few words about BGP, then we'll dive into the main topic of the day, which is the application layer. What we will see now is a few special things of BGP. Some of them are very interesting because like route flap dampening or damping is something that you can find in other contexts. Here is the problem. The problem is that every route change in BGP is propagated everywhere, like in any routing protocol. But because of the scale of BGP and the fact that it's global at the internet scale, there is always somewhere some change, which is okay, except if the changes are due to bugs. Typically a process that crashes is restarted, crashes again and restart, etc. So that kind of things, we all made experience of such things. It happens on routers. And when it happens, it creates a lot of traffic that is useless. And probably also it means that some of the useful traffic cannot be analyzed by BGP routers. What's the fix? The fix is a mechanism called route flap damping, which is explained on these curves. Here I'm illustrating on the time axis, the x-axis, events called W for withdrawal or U. So it's for a single route received by one BGP router. And then at this time here, the route has been withdrawn. Then an update has been reinstalled, withdrawn, reinstalled, withdrawn, reinstalled, etc. So that's a typical oscillation that you would like to catch. The solution consists in associating to every route a counter, a value, which is put in the adjacency rib in. When you receive a route, you associate it with one additional hidden attribute, which is this counter, which has the property that whenever you withdraw a route, in fact, you don't delete it, but you keep it, and you add a penalty to this. You add a penalty, a jump of here, for example, 1200, which is added to the value of this counter. And the rules are, when the value becomes large, then the route is embargoed. It cannot be used anymore. So the penalty increases whenever there is the withdrawal effect, which we saw at those 3 points here, and then it decays exponentially by using a moving average formula that is updated in principle continuously, in practice every few seconds. So let's see what happens here. The route is initially withdrawn, so its penalty increases. Then it's updated. When it's updated, then it's accepted because the value of the penalty is small and nothing happens to the penalty. The penalty continues to decrease. Then a bit later, the route is withdrawn again, so a second penalty occurs. Then it's updated and withdrawn again. But the third time the withdrawal arrives, then the penalty is above the suppressed limit. Typical values are the penalty is 1,000, the suppressed limit is 2,000. So if you have two suppression practically together, the route is suppressed. But if, like here, you have two that are not exactly together, there is enough time for the value to decrease here, and then we allow two withdrawal, but not three. At this time, when that happens, this route, which is withdrawn, is kept. Of course, it is also withdrawn, but it's made in embargoed state. It is the bit suppress is set to true, which means that whenever this route will come up again, it means this route or a route to the same destination prefix, exactly the same destination prefix, then it will not be considered, which is what happens here. Here the route comes again to this router, then it is not installed, so it's ignored, even though it's coming again. It's withdrawn again, which means the oscillations are continuing, and if the oscillations continue for a long period of time, then the penalty will continue increasing. We increase the penalty whenever there is a new suppression that comes, so a route that is truly oscillating will be declared inapt and will never be installed. Here, if the problem is fixed, the router is changed or permanently deleted, then perhaps this last arrival of the route here is the good one. There is no suppression, but it will need it will take some time until the exponential decay reaches below the reuse limit, which occurs here at this time t2. So we have achieved here a kind of what is called hysteresis. There is a delay in the behavior. If you withdraw and update a number of times, then the route becomes invalid, will never be used, and it will take some time of good behavior until it can be used again. So that's implemented in all BGP routers today, and that's a good way to mitigate the effects of undesired oscillation in a system. Another thing that we have discussed already is private AS numbers. So we have seen that every AS has a number, but like IP addresses, there are also private AS numbers here. Where is it used? Where here are two examples. A first one is if in a case like EPFL, if EPFL connects to a provider and wants to use BGP, if you want to use BGP, you need an AS number, because one of the mandatory attributes of a route is the AS path, and you need here to give a path that comes from ASY. But if, like in the case of EPFL, this client goes through the internet through a single provider, the rest of the world doesn't need to be bothered by the existence of this provider. So here you can use a private AS number, and then the provider will replace the AS number Y by its own AS number X in all the further announcements made to the rest of the world. So when they will be exported to the outside world, this will not be visible. So that's one mechanism that is also very much used to reduce the complexity of the internet. I'll skip this. Another use of this private AS number is to reduce the complexity of the IBGP mesh. Remember, the IBGP mesh is the fact that within a domain, all BGP routers have to be connected to each other by TCP connections. If you have a large domain with hundreds of BGP routers, which occurs sometimes also because you have more BGP routers than you would really need. Why? Why is that? For injection, for synchronization of the routes, to be able to put all the routes into the routing tables. We have seen that there are multiple methods that exist, but one of them that is very often used is that every BGP router directly injects into its forwarding table the routes, and that's it. Nothing else is done. And many ISPs do this, and if they do this, they need to run BGP in all routers, which artificially increases the number of BGP routers. All the backbone routers also have to run BGP here. So for this or other reasons, you may have a very large mesh, and if you want to optimize things, in particular if your network is structured, if you have groups of routers that fit together in areas, then you can cluster them. And one simple way to cluster them is to make internal virtual domains. For example, if you're an international provider that has presence in multiple countries and a few international links between countries, then it could organize its BGP network by having local BGP subdomains. And then you run eBGP between the subdomains. So everything is as if this would be a set of 3 domains, except it's only one. From an administrative viewpoint, it's all run by a single system. And when we talk to the outside, the paths that will be sent will always be with the ASZ, which is the true AS number of this domain. However, inside internally, we may use private AS numbers to identify the different subdomains. What's the benefit? Well, the benefit is that we don't need a full mesh. The full mesh must exist only in each of the subdomains. Of course, you need to make sure you have enough redundancy at the higher level here, so those routers are chosen to talk to other BGP routers inside their domain, outside their subdomain here. So here they run eBGP, even though from the administrative viewpoint it's internal, but it's eBGP from the sense of the rules we've seen, where the main differences between eBGP and iBGP is that eBGP does not make the assumption that we have a full mesh. So any route that is learned over eBGP needs to be repeated to all routers inside iBGP, but the converse is not true. So that's one of the tricks that's very often used. It's called a confederation. So this is Switzerland, and those are the cantons, if you want. To the outside, it appears as one single domain. To the inside, it's made of multiple domains. Of course, the AS paths inside the domain will contain things like P1, P2. They have to be removed by the output processing of the BGP routers that are at the border of the domain here. So a router here must have a rule which consists in saying, when I export a route in the output rib, I have to remove all the AS things that are internal, that are private numbers here. So that's another use. There are variants of this that I will not describe in detail. I'm not sure why there are variants. This seems to be a clean way to do it. There's another thing that keeps iBGP, but introduce explicitly additions to the iBGP protocol to elect cluster heads, and cluster heads speak for all the iBGP peers that are in the same cluster. Intellectually, it's exactly the same, but the protocol is a bit different. So both are found. This is called a route reflector. So the cluster head are called route reflectors. So, for example, a router that is here will not have a TCP connection to all the iBGP routers in the same domain. It will have a TCP connection to a route reflector, and the route reflector will talk to all the other route reflectors, and this is how they will repeat all the iBGP information. So functionally, it's the same as this. It gives the same, but the details of the protocols are different. This is also not very surprising and not very different. When you want to spread information between BGP routers, one way is to have everybody speak to everyone. But if your system is large, you may have intermediate hubs that will repeat the information and will do store and forward of the information. This is what is done here. Another thing that we often see in the internet is called route server. Route server is something to avoid the eBGP mesh. So what is the eBGP mesh? In principle, with eBGP, if we have a number of BGP routers that connect across domain boundaries, they don't need to be meshed. There is no requirement to have them. But there are situations where they are. This is in what is called interconnection point. Something has emerged to simplify the interconnection of multiple providers. The interconnection level is very large in the internet. If you're an ISP provider, if you're an ISP, you have to interconnect to a very large number of other ISPs. You cannot rely on connecting to a backbone provider that will do the job for you. This is not how it works for various reasons, in particular business reasons. So what has emerged is a number of companies that rent a room, a basement, and you've heard things like May West, May East. Those are the two big interconnection points in the US, where internet service providers come and rent some racks in such a basement, where they put a BGP router and where they interconnect to all the others who are in the same room and with whom they have peering agreements. So it's more efficient if you have hundreds of providers to have all the hundreds come to the same room and connect to each other, rather than having to manage every provider having to manage 100 different lines to all the peers it connects to. So it saves connectivity and it saves a lot of work. So here I'm showing, for example, 4 providers that are connected to in May West or May East, or in Switzerland there are also such points that I will describe in a second. Then each of those 4 providers can come with their own BGP router and connect to everyone. So here you need a very powerful switch network, so data center type of switching equipment. But still, if you have 100 of them, you start having, it's not a full mesh usually. It's not true that every provider connects to every other providers, but it's a very large mesh. Every provider connects to many, many other providers. Here it's shown as a full mesh. We have the same problem or the same optimization we can do with iBGP. Instead of having every provider come with their BGP router and establish 99 connections to the other BGP routers. You could put in the middle something which is called route server, to which everybody connects. So you can establish one TCP connection to this one, and here have the list of all the other peers to whom you would like to connect, so that you send to this one, again, a store and forward system, and this one can repeat it, of course, after screening who is talking to whom, but that is more efficient in terms of connectivity than having all this arrangement. Why do I talk about this particular optimization? Because this is typically the route servers that give us a view of what happens in the internet. Some of those route servers accept to publish what they see. And then it is in those points that we see who connects to whom. So this is, if you go to a number of websites that I mentioned, some of them, the information comes typically from route servers here. I will conclude with the last usual topic, security. So far, we have assumed everybody behaves well, and the ISPs are doing their job correctly, which is true largely, because an ISP is not anybody. It's a decent company that is accountable, that you can go against and sue if something wrong happens. But some ISPs are under the control of some governments, and they may do things against some other parts of the internet for political reasons. For example, some countries don't want that other countries talk about problems in their countries. So you can cite a number. Spain doesn't like very much that people talk about Catalonia, China about Tibet, France about Corsica, Russia about Chechnya, etc. Some of those countries have completely liberalized government where everybody can talk everything, some others don't. So there is interest of some to manipulate the routes. Here is an example of an attack that happened in the past. Assume here one ISP, ISP3 is malicious. I put it in America, but it was not in America. And it wants to attack EPFL. How does it do? Well, it sends into the internet a route to this prefix, which is one of the prefixes of EPFL. In fact, there's 128, 178, and 128.79. But switch, for us, advertises 128, 178/15. This is the normal thing to do that all IPv4 BGP tables will have in the world. Assume this guy pretends to be EPFL. The goal is to attract the traffic that goes to EPFL, for example, because EPFL is hosting sites about Tor or Bitcoin, something that is forbidden in this country, so they don't want that the traffic goes there, but instead goes somewhere else that will be under the control of this guy here. So, will it work? If ISP3 simply injects and says to its neighbors, I have a route to this and to that, what will happen? What do you think will happen? I close the poll. And the vast majority of you thinks B, some fraction of traffic to EPFL will go to ISP3. Well, the truth is I don't know, but A or B is possible. It depends on aggregation. Where is aggregation performed or not? Right? Because what will happen? The rest of the world will receive from ISP3 those two routes here. So say you're ISP2 and you receive those two routes. You've also received this route here. Or say you're ISP1. You receive those two routes and this. So those are three different routes, as we have seen. They have different prefixes here. So it depends whether they are aggregated by someone. Is there a BGP router on the path that has decided that those two currents should be aggregated or not? If they are not aggregated, that's the worst case for EPFL. Because if they are not aggregated, ISP1 will have those three routes. If the three works, if there is no connectivity problem, they are more specific. So all traffic to EPFL will match one of the two, and therefore will go to this guy. So in fact, if there is no aggregation performed, all traffic to EPFL will go to ISP3. In fact, it's a well-known attack against BGP by injecting routes that are more specific. And now here I'm injecting 2, but if I would be injecting even more specific, 128.128/something, where all the servers are, it's even more unlikely that it will be aggregated because it's only a little subdomain of EPFL. Then you will attract all traffic to this more specific prefix by the rules of BGP and longest prefix match in IP routers. Question?
Also, even on the AES path, for example, the decision process can decide not to accept those routes as the best routes.
Yeah, so the decision process, aggregation is after the decision process. So the decision process will receive this route, will accept them or not. And then when you export them, this is where you may aggregate. So somebody that accepts a router somewhere in the world that accepts the 3 routes might decide to aggregate them and say, well, after all, there are a subdomain of this, so I will aggregate them. But it's very unlikely if the routes are very specific. So if you have only this one and the path is very different, the question would be, how do you aggregate them? So it looks suspicious, but it can be done, and we don't control who does what exactly. But this can happen. It did happen, and that's a way to attract traffic. The attack in that case was against YouTube. So some government of some Asian country managed to attract all YouTube traffic to itself by doing that kind of attack here. If there is aggregation here, then it depends how the thing is aggregated. So it might be that some fraction of the traffic will go to ISP3, some will not go. So we have a problem, and this problem exists today. One of the ways it is solved is by having all ISPs make public, to a large extent, the routes that they have, and then if such a thing occurs, it will be detected, and then it will, if it's a single provider that does this, then it will be easy to find out that this guy is injected a route, this guy is not YouTube, while is this government injecting a route to YouTube. So when this is found, then all ISPs in the world will simply ignore routes coming from this guy because they're detected as bad. But some damage can be done. Ideally, in the longer term, we hope that BGP security will be implemented. So we have the very standard solutions you can imagine of, same problems we have seen with ARP. The solution is to authenticate everything. So if I send an advertisement, then ideally I should be able to sign it such that it can be verified whether it counts for somebody that has really the right to send this authentication. So there is some elements of this that's already in place. There is what is called public key infrastructure for routing. So that's the routing public key infrastructure, which can be used to authenticate the prefixes. And so you have, so with this system, a BGP message is signed, and then you can verify with the public keys that are available through this database. You can verify the signature and whether it has been sent by somebody who owns the private key that is associated with this prefix. So the problem is, in theory, fairly simple. The problem is the deployment of this, which is slow, and not all providers deploy this. Right? Also another issue that is often discussed, it requires BGP routers to verify the signature of all updates they receive. And many providers say they don't want to do this. It will slow down their BGP routers. Long term, it will not be sustainable, so crypto will have to be implemented. And but short term, this is where we are. I mentioned May West, May East. Here is the Swiss version of it. So if you decide to do a business on your free time of becoming an ISP, you will need to connect to other ISPs. You can go to Swiss IX, which is the Swiss version of May West, where you can connect to other providers. And as you can see, it's not so expensive. Here is the world seen from EPFL, or more precisely from switch. So those are AS number. You see 559, which is the AS number of switch, and you see all the systems that are, or when I collected this, it changes all the time, that are connected to switch. So those are AS numbers. You will discover a zoo of things, like you have providers, Swisscom, Service Industriel de Genève, British Telecom, a number of things connected to switch. And then you see whom switch is connected to. And you see that it's a very large connectivity, as I mentioned here. And you can do the same at the scale of the world, and you will discover the graph of BGP connectivity. Very often when people do papers of social sciences about the connectivity of the internet, the thing that they describe as connectivity is the BGP connectivity, which of course is not the same thing as the connectivity of the internet. I mean, Switch is a relatively small provider in the world compared to one of its peers that might be US Sprint, for example. So this graph don't tell you really the map of the internet, they just give the relationship here. I will conclude on this slide that is showing the number last week of, or 2 weeks ago, of the number of IP prefixes in one of those route servers for IPv4 and IPv6. I should put a better light on this. Right. So what is striking is the scale difference. There's a factor 10 difference between IPv4 and IPv6. And you see that IPv4 is close 800,000, so we're close to 1 million. So as long as we have a lot of IPv4 in the world, we have a problem of performance with BGP routers. So we have to make the BGP routers really powerful because they are manipulating tables that are close to 1 million entries. And whenever something changes, you may need to revisit the best routes for each of those 1 million entries here. So that's essentially the problem of BGP today. With IPv6, we hope it gets much better, as we mentioned, because of aggregation. With IPv6, we're able to dramatically reduce the number of routes because of the more structured addressing scheme that we have in IPv6. Voilà. There are pointers in the slides. There are other slides that don't show where you can have fun and go on the internet to look at how the internet is live today. Any other questions? No? Then we move to the next topic, which is the application layer. A radically different topic. The application layer is not really the focus of this course. So what we will discuss on this course is things related to networking that are visible in the application layer. Of course, the most interesting thing in the internet is the applications. But the applications themselves are the topic of other courses like distributed systems or even software engineering. This is the fun part. But we will talk about a few topics that are still fun. The application layer that started the internet, or that made the internet famous, is the web. And it illustrates here all the things we know about the web. The web emerged in '92, became popular in '94. Before that, the internet existed. When I was a student, I used the internet, but with clumsy things like FTP and sending mails by typing words in a terminal and making sure you have with the line editors, for those of you who know VI, VIM, with that kind of things, and you type a line that has simply a dot in it, and that means end, and you send the mail. So there were those things existed, but they were very clumsy. Because they were clumsy, very few people used them. When the web came, this made that kind of things here, whereby we could have an indirection where we could go from from a single user agent, you could aggregate content from various places without knowing anything of the internet, just click on things. When this was developed, it was called HTTP1. HTTP1 used one TCP connection per object, which makes sense because when you transfer an object with TCP, you have no information on the beginning and the end. So if you have a page that has embedded objects like images, banners, sounds, style sheets, at the beginning there was not much of this, but still there were already some of it. Then the easiest way to program was to do one TCP connection per object. So on the server side, you would send an object, then the object contains a page. If the page there is something else, you open a new connection. That was HTTP1. Of course, it's not very efficient. It was very efficient when a web page was essentially one style sheet and one text. Then you have two things to transfer. A web page today is loaded with a zillion of things, including commercials and hidden robots that spy on everything you do. So all those objects, it's not efficient if you have to open one TCP connection for each of them. Why is it not efficient to have multiple TCP connections? Yes?
Because it wastes resources of the server. The server has to open a TCP connection for each space. Because of TCP congestion, it's not small. So it's installed first.
Correct. So it's not very efficient on the server side because the server is burdened with a large number of TCP connections to open and close also. You know, when you close a connection, it remains closed for some time, even when it's not used, so it's still using kernel resources. Also, from the congestion control viewpoint, when you open a connection, you start in slow start modes with a small rate, and then you increase the rate. But if you do that 10 times, you always start small, instead of having to transfer a big thing one after the other. So HTTP2 does this. It allows to use the same connection for several objects here. Right. Now, if we use HTTP2, and one packet of the first object is lost, what will happen? I close the poll in 5 seconds. And the correct answer, unfortunately, is B. So we said it's inefficient to use, we said it's inefficient to use multiple connections, but there are also drawbacks in using a single connection. Nonetheless, this is what is done today. If you go on the web, with one exception that we'll mention in a second, you probably are using HTTP2, and this happens exactly. So if there is at the beginning a loss in slow start, for example, that will take a lot of time for the first object to be transferred, then the entire page will have to wait a lot of time. And we experience that. We experience some randomness when you go to a web server. Once in a while, it takes a large amount of time compared to the average. That might be one of the causes. This is what we had called head-of-the-line blocking. That's the property of TCP. That when TCP is used to transfer multiple things, it insists on delivering them in order. So if one piece is missing of the first object, which is your style sheet, for example, or even worse, a banner that brings zero information to the page, but it's just there because they insist to have their logo on every page. So the first thing that comes, and the rest you don't see because you wait until you repair the banner, which may even be an animated GIF or things like this. So that's one of the problems, and we'll see how today it can be mitigated, or what are the new things that will come to avoid this problem here. Oops. Another question about the terminology that we've used a lot. Here is an example of FTP. So we should not use FTP, we should use SFTP, but this is simpler to explain with FTP. FTP can be used in this mode or in that mode here. In this mode, With FTP, FTP is opening a remote shell on a machine over which you send commands to send or download files, or even move and delete files. So you first open a TCP connection, and over this TCP connection you will send requests like get a file or put a file, and for every file it will open a TCP connection. Now the TCP connection in this case is opened in this way. That's called active mode TCP. There's another version called passive mode TCP where the opening of the TCP connection is done in the other direction. Both options exist in FTP today. In this diagram, which of those port numbers are TCP server ports? So 20, port 20, where's port 20? Is here. Port 21, port 1, 2, 3, 4, 6. Those are the 3 ports of interest. Which of those are server ports? I close in 5 seconds. And the majority says D, 20 and 21. No, 21 is a server port. What's the definition of a TCP server? What's the definition? Well, remember lab 3, you've coded socket programs. So a TCP server is something that's waiting for a connection to come, for a SYN packet to come. So this is a server, it's waiting for the SYN to come. 20 is not a server port. It's a port on the FTP server, but it's not a TCP server port. In fact, here, you instruct the server to open a connection to you. So the server port is this one. So the logic of the FTP code here must be such that after sending this instruction to the server, you must do a listen on this port, 1, 2, 3, 4, 5, 6, or whatever ephemeral port number the operating system gave you. So this is a server port, this is a server port, this is not a TCP server port. So the correct answer is F here, which today is not receiving a lot of support in the class, but that's the correct answer. That's a small subtle difference between what it means to be a server here. Of course, why it is done this way is not very clear, but this is how FTP was done. Many firewalls prevent opening TCP connections to ports other than specific ports on specific machines. So very often that doesn't work. This is why there's a more usual way of doing things where you talk to the server and then the server gives you the information on which port you should now open the connection to download the file. So when the logic here is such that the FTP server now opens a new socket, and on this socket gives you the port on which you should do this. Security is, of course, very important in the application layer. Perhaps it's the layer at which it's most important. In Lab 3, those of you who did the last part played with TLS. So the standard way to do security at the application layer is to do TLS. TLS is what we see when we use HTTPS. HTTPS means we go to a server that is authenticated. So TLS adds encryption and authentication on top of TCP, which is, of course, what you'd like to do. If you go to your bank, you want to be sure you're talking to your bank and not to a man in the middle that's intercepting all the transfer order that you're given and will repeat them to the bank, but with a change of destination, for example. So you've paid your bills, but not to the right company, so you'll be in trouble. You've lost the money and you'll have to pay again the bill plus the fees for being late. How is that managed? Well, typically, we've spoken already of digital certificates. Digital certificates are things that are signed by a trusted entity that contain the public key of the bank, for example. And my web browser has the public key of the trusted entity. So when the bank talks to me, the first thing they do over HTTPS is to send me the server certificate. So I will receive the certificate of the bank, which contains the public key of the bank, signed by the private key of the trusted entity. And since my web browser has the public key of the trusted entity, it can verify the signature. So if the trusted entity is trustable, which is yes, another story that we won't discuss. So after this phase is done, I am sure that the thing has been signed by somebody who can claim to be my bank. And then after this is done, there is typically a number of messages to agree on the crypto system that will be used to encrypt everything. So we talked about the authentication phase. Encryption is typically, could be used with the same asymmetric cryptography techniques that are used for authentication, but it's only in theory. It's very heavyweight. The compute time to generate cipher text using asymmetric cryptography is much, much larger than using symmetric cryptography. So symmetric means a shared key, a secret key, is negotiated between the two parts here. So for example, in TLS 1.2, the client sends secret key information that is compounded by secret information from the server, and at the end, using a number of possible mechanisms, there's a large number of different mechanisms, and I will point to the security course to discuss all of them. Diffie-Hellman is one of them. At the end of this exchange, both parties agree on a secret, which is the secret key that will be used to exchange all information. And this guarantees that a man in the middle will not be able to get the secret key thanks to the initial phase of authentication here. So that is how, in practice, we use the application layer today. Not all websites are using HTTP, but practically all are using it. Otherwise, if you don't use HTTPS, you have no guarantee which site you're really going to. Now, if we use HTTPS with this version of TLS, how many handshakes are required before data transfer can occur? So when my web browser connects to my bank, how many handshakes? So handshake is a round-trip delay where I exchange a message and I get a response back. So how many of those things do we need before I can start even talking to the bank by saying get the home page, for example? I close in 5 seconds. And the majority is a bit optimistic. If we look at all the details that we've put together, we should not forget TCP. Right? First, you have to open a TCP connection, which means SYN, SYNAC, and if you're lucky, that's only one handshake. You still have the third packet, but if you're lucky, you can incorporate that in the data that you're sending. And then you will need all that zoo of TLS.1, which is at least 2 round-trip times. So the minimum you have is 3 round-trip times. In some cases, even more, depending on how things are. So with TLS 1.2, it takes 3 round-trip times before sending the first get. So before you get to the home page and see something displayed, you have done 3 round-trip times. So that's the price to pay for HTTPS. Plus, of course, you have the processing. Well, we will see after the break how this motivates other solutions to get rid of some of these delays here. So we do a break and we resume in 13 minutes. Okay, we're ready to restart. So this means that if we combine the head of the line blocking, the 3-way handshake of TCP with HTTP2, the time to do the handshake with TLS, there's a large latency before doing anything. So that's a problem when you do interactive transactions. When you download a video file, perhaps you're willing to pay for this overhead, but if you do a lot of interactive flows, which is very often what happens on the web, there is a performance penalty, which is the state of affairs today in the internet. But there are solutions. The first solution is to streamline TLS, and this is being done by the new version of TLS 1.3, where after more careful engineering of the protocol, which involves removing some of the cipher suits that require very complicated handshakes, it's possible to do the TLS handshake in 1 round trip time. So that's the first thing that will be coming. So instead of 2, so we save 1. Sometimes even in 0, if you cache the pre-shared keys that are exchanged here, but there's lots of discussion on that. I'll let you discover that in the slides. So that's only one part of the story. The other part of the story is to integrate everything in avoiding to do TCP, then TLS, then HTTP. And this integration is called QUIC. It's done by Google. So if you use Google software, Chrome, or a YouTube app, you're probably not using TCP when you go to the internet. So we have discussed, and there are many questions that many of you have asked. I mean, why does TCP do things the way it does? Why is it doing head-of-the-line blocking and per stream? I mean, being reliable doesn't mean that we have a stream. And all those questions, they are valid. And if you want to do things differently, well, you do something that is called QUIC. So what is QUIC? QUIC is a transport protocol, intellectually. If you want to be dogmatic and formal, it is not a transport protocol because it uses UDP, and UDP is the transport protocol. But still, it's performing all the function of a transport protocol. But the first new thing is that it does it by incorporating the security handshake. So when TCP was invented, security was not an issue. It was not even envisioned that we would need things like cryptography over the internet, believe it or not. This is how things were. So TLS came on top of TCP, and then HTTP comes on top of TLS. So we've stacked the things one over the other. But today, any connection you open to anywhere must be authenticated first, practically, or should be authenticated. So you want to have authentication always, and very often also encryption. So the first thing you want to do before talking to anybody is open all the TLS stuff. So you don't want to do the handshake of TCP before. You want to do this opening of the connection before, of the authentication before. So you want to integrate the security inside the protocol. So that's the all-in-one design of QUIC. So QUIC, before doing anything, it's like TCP from the sense that in order to talk to someone, you first open a connection, a QUIC connection. But a QUIC connection is a TLS session. It is the exchange of authenticated credentials and of key material for the encryption. So that data is always secured over a QUIC connection. Now QUIC runs over UDP. That's, if we would redo things today, if we would do from scratch the internet, QUIC would be a transport protocol like TCP and UDP, so it would run natively over IP. But for many systems, that doesn't work. There are systems in particular for which that would cause problem. Which systems are these? We have seen them. You have played with them. If Google would reinvent QUIC as a new transport protocol, it would not work. Why? So the NAT. Yes, exactly. So the problem is the NAT, exactly. So if you would do this, your NAT would see something unknown, a new protocol type, so it would not work. So if you change the software in Chrome, for example, so you update a new version of Chrome, it doesn't work because you need first to change also the software in your NAT. Of course, you don't want to do that because the NATs are a box that you don't change the software, in fact, or you don't touch it. When Swisscom does it, you don't know how. Probably nobody does anything to that box here. So that's called the ossification of the internet due to middle boxes. There are things like NATs There are other things that are done in mobile networks that look at the protocol type and the port numbers to do a number of optimizations. So in order to be compatible with that, any new protocol you do today has to be on TCP or UDP. You don't want to do it on TCP because you want to fix the problems of TCP, so you do it on UDP, which will make you compatible with all the NATs here. There's another reason also, which is more subtle. It is that the transport protocol is typically part of the operating system. In Linux, it's part of a module, or it's a module of the kernel. In Windows or Mac OS, it comes with the operating system release. If you change TCP, it's a new version of the operating system, typically, which is very heavy, and for Google, for example, is not desirable because Google doesn't control all operating systems, not yet. They control a large number of them, but not all. So if they want me to use Chrome with Quick, and if I use an iPhone or a PC with Windows, then if they require Microsoft or Apple to do it, then it won't work, or they have a chicken and egg problem. So having everything as the application layer makes it also easy to implement. So in fact, if you use Chrome or YouTube today, you're using Quick, but you don't realize. So you use a new version of a transport protocol, but this comes bundled with the application program. Incidentally, it's also much easier to develop code, for those of you who've done it, in user space than in kernel space. And developing in kernel space is a nightmare, and debugging everything is very complicated, so your productivity in number of lines is divided by 10 compared to user space. And when you crash a kernel, it's not funny. So this is why it is the way it is here. So here's what happens if you use the best of TLS, but perhaps not the best of TCP. If you use standard TCP in order to open something, you will first do the three-way handshake of TCP, then you will do the two-way handshake of TLS 1.3, and only then you can send a GET here. This is the best you can do today with TLS 3. It's not exactly the best. We've seen that with TCP, there is even a better thing we can do, if you remember. There's one option in TCP called the fast open, TCP fast open, TFO, which is a little trick invented by Microsoft I believe, by Microsoft, to avoid the SYN ACK. But this is for a client that is repeatedly talking to the same server. If you repeatedly talk to the same server, the server can send you a hash of your IP address and a secret kept in the server, such that when you will send the SYN, you send this hash as an option in the SYN, and then the server knows it is somebody who is a legitimate user. It's not a spoofed IP address, so I can immediately start sending. If you use this, then you save this, you simply have a two-way handshake, which is what you get with Quick. Also, but here you get, even if you're not talking to a server repeatedly. So the first thing you do with Quick is open the security channel. And once you have a security channel open, you can send a GET. So one handshake of overhead, and that's all. Right? Quick also assumes a number of things to make its life easier. For example, one of the problems in TCP is also might be to negotiate the packet size, because you don't know which packet size will run on the internet. But most of the things today, if you're not using exotic things like TCP over Bluetooth or things like this, then you have an MTU which is at least as large as that. The MTU is 1500 in principle. It can be less because of a number of things. For example, when we use encryption, then the encryption takes parts of the payload, so the useful part for the data is less. If we encapsulate, if we send a packet in a packet, so a very safe lower bound is this one, and it assumes this. If it is not true, it will not work. But if Quick doesn't work, well, you'll use TCP as before. And you can try it with Wireshark if you use Chrome, for example. Inside Chrome, you can also verify that. So how does Quick solve the problems of head-of-the-line blocking? Well, very simply, by decoupling the Quick connection from the stream. So we can view TCP as a Quick with a single stream. QUIC allows to have multiple streams. Right? A stream is like what happens on a TCP connection, and a QUIC connection can have as many streams as you want. There is no overhead in creating a stream. You can simply create a stream by sending data and a new stream number. There is a numbering scheme to make sure that streams that come from the server or from the client have different numbers, but that's all. So you can simply create a stream by sending a new packet in this stream. So if you're going to an HTTP server and the HTTP server responds with downloading a number of objects, it will create one stream for each of the objects. Then the streams are sent in a packet here. And everything that is in TCP is in TCP header is in additional elements that are inside a QUIC packet. So for example, the acknowledgement field is just a field in the QUIC packet. So it's not a fixed size and a header, so we don't have all the limitations that we have in TCP. In TCP, originally acknowledgement was just one number, the ACK number. Then people realized that, but it's not very efficient because you may have lost some packets and not others, so we can send SACK, but that's a TCP header, so the TCP header cannot be too large, so there's at most 3 SACK blocks. Here there is no such limit because it's part of the data that's in the QUIC packet. So an ACK field can have a very complicated, is able to express exactly the missing data here. There is also all the things we have seen in TCP. So everything we've learned about TCP is done in QUIC, except now we have multiple streams per connection. We do flow control, for example, per stream. So flow control, remember, is about preventing a source from sending too fast for a given destination here. So that function must still be present, at least in most cases, and you do it per stream. There's also one flow control per connection. It's not using a window, it is simply saying what's the max offset number. So in a stream you number all the bytes, and flow control says you cannot send me more than the next 200 bytes. But there is no concept of a window, and it's both per stream and per connection. Of course, it also does congestion control per connection, exactly like any application that is using UDP must do, and it does exactly the same thing as TCP. In fact, there are multiple versions of QUIC. There is the first version of QUIC, the one that you find in the Google software, that uses TCP cubic congestion control, exactly. So it implements the same verbatim, the same thing as cubic. There is a version of QUIC that is being standardized by the IETF that specifies it should do TCP new Reno today. Okay, so Apple, Microsoft, Facebook are developing their own versions of QUIC that will probably use TCP Reno. Right? And last but not least, you can also, at least in theory, I haven't seen much practical development, but in theory in QUIC, you can also have unreliable streams for applications for which, for example, streaming application of sensors, devices that send information and repeat the information very quickly, such that, of course, you care about receiving the information without error, but if there's an error, there's no point repeating it. Stream does repetition exactly like TCP. QUIC does repetition exactly like TCP. There is a packet number, so every number, every block of data that you send that contains stream data has a packet number, and then there is an acknowledgement for the packet number for the packet. So every packet that is lost gives you exactly the information about what is missing, and this information will or will not be resent. It will be resent for all the reliable streams, but if a stream is declared non-reliable, it means there's no point resending, then you don't resend. And this could be the case for sensors that refresh the information very frequently. If the information is lost, you will prefer to send new information that's better and avoids the head of the line blocking. Of course, with all those things, QUIC is more powerful, but it's also more complex. We've seen there's lots of options. And in particular, one option is on the quick sender side. If you have 4 streams and you have to send 4 pieces of information, and in which order do you send them? You may need to create 1,000 packets, because that's a lot of information. It's used by YouTube, for example. So it's not one stream is audio, another one may be video, another one may be the subtitles. One stream is the control. This is used for opening the connection and doing the TLS handshake. This one always has priority. But if you have more than one packet to send, in which order do you send it? So if you do quick socket exercise, if you want, you will need to do something we did not have to do with socket, which is a scheduler. You will need to decide of the different streams in which order you send them. It might be FIFO by default, but it might be something else depending on the logic. So it will be considerably more complex, but also more powerful. Voila, so that is the what the Internet is developing. So as you see, even though those things are very old, it's always changing. Congestion control is changing. The transport layer, even though we don't call it formally the transport layer, but at the ITF, QUIC is discussed in the group that is called transport. So we can still view it as transport layer. When QUIC has stabilized a bit, perhaps in the next edition of this course, I will put it in the transport layer. So lots of things are in flux, and many people conjecture that QUIC will largely replace TCP in the coming years. The good news is all the elements of QUIC are exactly the same as TCP, except for the fact that there are multiple streams per QUIC connection. Voilà, our next topic is to go a bit more in depth into something we have visited already many times, DNS. The DNS, of course, is at the heart of everything because we use names everywhere. And we've already mentioned that the goal of DNS is to map names to addresses here. So the mapping is based on an ontology, which is a tree of all the concepts. Originally, at the heart, so at the beginning of the internet, when the internet was simple to understand and was done by engineers only, there was only those domains, 3-letter domains. The most famous is .com. Edu is practically American universities, government, which means American government. Military means American military. .net means any entity that has to do with the internet itself, and org, any non-profit organization. And then there were the 2-letter top-level domains that were and still are countries. So 2-letter are countries, 3 letters are the top domain. And then, the commercial people, the business people came into it, and they found that there's a huge amount of money you can make by selling names. So you can now invent any top-level domain, like firm or sucks even has been. So if you go to apple.sucks, it works. And this is an example of the exaggeration that leads to somebody bought and created the .sucks domains, and that then blackmails all the company by saying, you need to buy a domain from me, because otherwise I will make a site called apple.sucks, and then, so Apple wants to control this one, right? Not someone else. So there's a lot of discussion, and it's not very clear whether it was a good idea, but this is where business leads to. If you do something like this, it will cost you $500,000 a year to maintain such a name, right? So, whereas if you buy a name from CH, it will cost you, I think, 15.5 francs a year to maintain such a name. So, of course, the prices are different. The names can be originally were, of course, English names, but you can have today any other characters using things like Punycode. For example, one of your predecessors once put up a website that was called EPFL. He was Swiss German, and this was pre-Facebook, so it contained all the for students only information of EPFL, like last year's exam with solutions and things like this. Right? How does it work? How does the mapping from name to an IP address work, which is the gist of the DNS, how to map a name to an IP address, right? Well, it's done. The simplest is to look at this example here. So as we know, every end system, PC here or a smartphone, has to be configured with the address of a name server that will accept to provide service to this one here. Typically, it's part of the configuration we obtain from DHCP, for example. In the past, it was difficult to get a name server that works for you. In fact, only your ISP was accepting to work for you. But now companies like Google, again, accepts to open their web server to everybody. So if you use 888 or 444, those are Google domain name servers that accept to work, to do the work for you, because they will get a lot of information about what are all the queries that are sent. But the traditional thing is to have a name server of the entity that provides you internet service. If you're on the EPFL network, it's an EPFL DNS server. If you're at Swisscom, it will be a DNS Swisscom server. So whenever you have to resolve a name, which occurs, for example, when you click on a web page that has an URL that is a name here. So URLs are typically the first element of URL is the protocol, HTTP or HTTPS. The second element is a name, which must be resolved to an IP address. So when this is resolved, your piece of your operating system, called the resolver, will send a query to your configured name server. So it will send a query here with a flag called recursivity desired. We will see what that means. And is saying, I want to have the address that corresponds to the name. The A here is a symbol that is alluding to the type of a DNS record. We can view the DNS as a big database, big tables, that a row in the table is a name, an address, and such a row corresponds to what is called an A record if the address is an IPv4, a quadruple A record if it's an IPv6 address. So they're considered different records. So here I'm asking, what is the IPv4 address of this machine? I asked the EPFL name server. The EPFL name server doesn't know this address because it's Zurich.ibm, that thing, and perhaps it doesn't know. The DNS server of EPFL knows all the IP addresses that correspond to all names of EPFL, because it's under the control of the entity called EPFL that has obtained the authority about all the names that end in epfl.ch. But this one is not in that domain, so perhaps it doesn't know. Perhaps it knows because it has cached it, but perhaps not. Here I'm assuming it doesn't. If it doesn't, it will relay the query to another name server that will be able to give the information about this one here. How is that done? Well, first we see that here we had recursivity desired, and the recursivity is exactly what happens here. This server is keeping the request, working on it, and will respond only when it has solved it. This is called recursivity desired. So it's doing a good service to you here. And typically, only the servers that provide the service to the end customers do that. Now, when you talk to another, when this server talks to another server, between servers, they don't do that kind of thing. So it will be iterative. Iterative means, in the worst case, where this server really knows nothing of the world, it has to know the IP addresses of what are called the root servers. The root servers are the servers that contain the information about the top of the hierarchy, typically the three-letter systems here, and also some of those here. So this root server, contacted by the EPFL server, receives this query, which is the same, except for the recursivity flag. It's again asking the same question, but since it's a root server, it will help by saying, I don't know the answer, but I can help you one bit because I'm a root server. I know where is the DNS server, or one DNS server that can help you with the IBM domain, ibm.com. So it will respond with a message saying, here, the question was this one. I don't have the answer, but I have some more information, and the information is the name server, so another record in the DNS, NS, stands for a name server. This server is the name server for EPFL. Here are the informations about the name server of IBM.com. The two name servers, they are given by their name here. Of course, their name is not useful. We give their IP addresses here. So here, we are giving, in fact, 3 IP addresses to this guy of domain name servers of the IBM Corporation. So now the EPFL server will send the same query again, but now to a different machine. For example, it will pick one of the 3, probably the one on the top, and will send the query. And this guy being at IBM will know and will respond with the IP address here. So this is, all those things might happen. So we talked of 3-way handshake, but if you need to resolve the address, you will have all that thing before. Of course, this is a worst case here. I'm assuming this server doesn't know where is the IBM domain name server and doesn't know this IP address. But of course, all of this will be cached if a similar query comes again. So if someone else comes with another question that has to do with IBM, then we can ask again, we can skip this phase. And if it's exactly this, the same name to be resolved, we can even skip and have immediate response. And even sometimes in the machine, the most processes will keep a cache of all the queries that were sent previously. So your web browser, until you kill it, will not resend queries again. So you can use programs like Dig, and we've done that in the past, to look at what's in a web server. Here, for example, I went to the web server, to my DNS server, and asked, give me all the information about lca.epfl.ch. And we see that we receive some information which contains the IPv4 address of this machine. If I send the same query with quadruple A, I will obtain the IPv6 address of this machine here. All those queries contain also a quantity that's called the time to live, which is a real time to live. Not like in IPv4 where the time to live is a hop count. Here it's a real time to live. And it has to do with the caching. I said when a server or even a client has had already an answer to something, it will keep it in a cache. Now the question is, how long do you keep it? And the answer is the DNS servers that control that. So DNS server, when it sends you an answer, it will tell you how long you should keep it. EPFL, for example, keeps, the EPFL server has TTL 1 day. So whenever somebody asks, then it will keep it in a cache for 1 day. Google has a time to live of a few seconds. Why such differences? What's the advantage of having a very long or very short time to live? Yes?
Well, I think it looks more static. If we add some more IP addresses to have. So it's a smaller, let's say, domain that we can reasonably control, but Google has to control everything else, which is much more fluid, and changes can happen very frequently. But the downside is that we need to update the whole table so frequently.
Exactly. So the difference is at EPFL, we're not in the business of providing internet service, content services to the world. So what we want to minimize is the work and the power consumed by the DNS server. So you don't want people to bombard every second for the same question the DNS server of EPFL. You may want to save on those resources here, and that goes with the assumption that the content is fairly static. The content of Google is more dynamic in the sense that if I go to YouTube, for example, my browser will first go to the DNS to find what's the IP address of YouTube, and this IP address will change all the time, because Google has 50 data centers in the world, and I will be directed to one of the nearest. If I redo the same thing 10 minutes later, I will be directed to another one. And there may be failures, and there may be time of the day traffic management. That's called load balancing. That's one of the things that DNS can be used for. We'll talk about that in a minute. So this field is present in all records. And for example, here, IBM does 2 hours. That means when this information is received, it will be kept for 2 hours. And if a new query comes after more than 2 hours, then it will trigger another request here. So let me skip this one. Sometimes we do also reverse DNS lookup. In fact, we did it when we use ping or traceroute, and we don't activate the option to show only numerical results. Here, Lisa is doing a traceroute to this, and you receive an answer that's in the form of names. So you receive all the names of all the machines that are on the paths. Right? Of course, the names are not in the packet header. We know that traceroute works by sending packets that have increasing TTLs, and the TTL are too small, or the hop counts are too small. The packets are rejected by routers that send error messages, and the error messages contain the source address of the router that sends the error messages. And what is displayed here is the source address, but also the name of those routers. So when doing this, of course, traceroute, it's traceroute that does the work of finding what is the name that corresponds to the IP address. How do you think that it does it? I close the poll in 5 seconds. The majority says B, but it's not exactly correct. If you think about it, here it's searching the database. I mean, how would DNS clients, so it's almost correct in the sense traceroute has only the IP address, so it has what is called the reverse DNS lookup problem. I have an IP address, I want to find the name. If I have one database, one big table on my computer, I can do a reverse search. That's standard things all databases can do. But DNS is not like this. It's not one database you have on your computer. It's distributed everywhere. The information about the IBM names is on IBM server. The information about the Google names are on Google server, etc. So if I want to search this, I need to search all those databases. So I would need to send robots everywhere in all servers that themselves will search them. And large companies may have even subdomains. If I search, IBM might have subdomains, for example. So that is conceptually possible, but would be very hard in terms of resources, and also perhaps would not work, because I doubt that IBM would allow you to search their database. Right? So I don't think they would accept a packet to come and say, find me in my DNS servers all the things that have this property. And they typically don't want to let you do that. So for security reasons, you don't want arbitrary functions to be done on your data. So that would probably not work. And the other things don't work. So the correct answer is none of the above. And the none of the above is a very primitive thing, which is simply that when you put a name in the DNS, you also put the reverse mapping with another record, which is a reverse record, which is a PTR record. PTR stands for pointer. So when you put in the DNS that the name like www.epfl.ch corresponds to an IP address like this, you also put a reverse record, and the reverse record, if you want, formally corresponds to a tree that is structured by numbers. So you search the tree by saying everything that starts with 128, then 178, etc. here. So that if I go to the server, to the DNS server of EPFL, I will find that, for example, there is a record that says that the IP address 128.178.15.1, it's translated to the style of DNS names. The style of DNS name means that first you put a top-level domain that corresponds to all IP addresses, IPv4 addresses here, and then for some reason it's in the reverse order, because DNS, well, I don't know why, but this is written in this order, and then you will find the name. So you have to have two records. There is no guarantee that the records are consistent. If there is an error in the DNS file of EPFL, and you put in the pointer record this name and this address, but in the A record you put a different combination, then things won't work. whenever you will do a reverse query for this IP address, you will get the wrong name here, right? So here, that's not the case. Here I asked, what is, using dig, I asked, what is the name that corresponds to this IP address? I got this answer. If I ask, what is the IP address that corresponds to the name, I obtain the same. But if you do in different cases, here, there are some funny domains that, for example, have found weird names that don't correspond at all to the addresses here. Yes?
Are there any practical dangers where this would be a problem? I mean, this use case for trace route is not.
Yes, of course it's a problem. Any inconsistency is a potential problem that could lead to attacks or to things that don't work.
What are the use cases of inverse besides, let's say, trace route where you want to see the actual next corresponding address?
Very good question. What are the practical use cases of a reverse lookup? It's essentially debugging. Traceroute being one of them. So who manages all that stuff? I said there's nobody that manages the internet, but DNS is managed. So there is a top-level authority that manages the names. So now there is a distinction in the internet in DNS between the management, the legal management of names, and the management of selling the names to you and me and other people. So there are what is called registries. For example, in Switzerland, there is one unique registry, which is an authority that receives delegation from the Swiss government to be the authority for all names that correspond to the domain .ch. So every country has a two-letter domain, and every country is supposed to have one government, and the government nominates one organization that manages this. In Switzerland, it's Switch here. But it's just a legal thing. They decide who can do what. If you want a name, softcom.ch, you have to buy the name from someone who will send you a bill every year, and that commercial part is done by a different entity, which is called a registrar, and there are hundreds of them that are able, and they don't need to be Swiss. You can buy that from a German company, for example. You need to pay for them, and they essentially have a database saying who paid for what, and they manage the bills, essentially, which costs a lot of money. So you pay, essentially, in order to recover the costs of making sure that you pay. After that, you have your name, for example, softcom.ch, and you still need to put it in a DNS server. If you're EPFL, you have your own DNS server, so you put epfl.ch in your DNS server. If you don't have your DNS server, you need to find a DNS hosting company, nearly free speech and things like this, that for a few cents a year will put your name into a DNS server. So this is all the zoo of all those things that makes the name system work today. Of course, the key thing is the authority at the top. Who decides that .ch belongs to Switzerland, right? So this is originally it was an American company, not-for-profit company that controlled everything, and now it is being run by an international consortium that is trying to bring the interests of all parts of the world into that. And this new organization has decided to open all the names to whoever wants. So if you, like you mentioned, .sax, which was kind of a scandal when it appeared, but you can buy the name of a company, Coca-Cola, for example, you can buy your name for this here. We'll see what happens in the future. This is not always very useful. We've mentioned one interesting function of DNS, or one side effect. DNS was originally invented in order to have, DNS was invented well before the web. So before the web, finding a service on the internet was very difficult. When I was a student, I had little books. When you would write, it's like when you have your Linux how-to, you have lots of things that you need to type. How do I set the keyboard to Swiss French? Okay, so you have to write all of this. So the internet was like this. And it was much easier if you had names than IP addresses. In order to send a mail to somebody, I go to a given thing that has a name. And so the idea was to have a human readable naming system for resources. Now, to a large extent, this is no longer very useful, because if you search for something, you don't go to your little booklet with the name that you have written. What do? If you search you want to post something somewhere, you want to go to your bank, and do you have written exactly the HTTPS of your bank? You use Google search or Bing search or whatever. You use a search engine that will get you to that place. So because of search engines, in fact, maybe some people say we don't need DNS names. We could as well identify something with an IP address. That would save a lot of this DNS thing. But some others make the observation that DNS is still used for things like load balancing. That's one example that we have mentioned already. Here I put it with softcom, but replace softcom by Google. If you want to go to google.ch or google.com, then it's very useful for Google, who doesn't care about the computing resources, because the EPFL wanted to have little traffic on the DNS server. Google is happy to have a lot of traffic on the DNS servers. So what they will do is they will have very dynamic DNS servers that will have many, many addresses for the same name. There are different ways to do it. A simple way is to say, I give to this company a large number of different addresses and a fairly short time to live. So that's 300 seconds. It can be even much shorter. And then I can change this regularly on a round-robin fashion, for example. Or also, depending, I can even have some logic that says, depending on the IP source address of who sends me this DNS query, I can give a response that depends on whatever logic I have here. So that's a way to share the load by having users go to different IP addresses here. As usual, security. DNS is a very sensitive part of the internet. If I go to my bank by typing, I don't know, bcv.com or .ch, if I go to somewhere else because a rogue DNS server is sending me the wrong address, then that's the first element to mount a man-in-the-middle attack. And it is possible today. So you should not trust, in principle, the responses necessarily obtained by DNS. This is mitigated to a large effect with TLS. We have an authentication of a thing at the end, but it would be better to have more. So there are solutions similar to BGP security, is to have all the records signed using a similar public key cryptography infrastructure, where the root certificates can be put themselves in the root servers of the DNS here. So this is done by some domains, like Google does it systematically, Sweden does it, but not all domains do it. Alternatives are to use TLS to the DNS queries. DNS queries use UDP, not TCP. There's a version of TLS called DTLS that works over TCP, over UDP, so you can authenticate at least the DNS server, so to be sure that the DNS server to whom you're talking, for example, when the DNS server of a PFL queries a DNS server that pretends to be IBM DNS server, then it's fairly easy to verify that this is really IBM by using certificates. So this is also an alternative, and there is a current work on doing DNS over QUIC, as you can imagine, because QUIC can do everything. Voilà, we'll stop here for today. See you tomorrow.